new on Curiosity Stream.
I'm James Burke. I'm going to take you on a journey through time.
James Burke's visionary series returns, reimagined for our time.
Now, this is all uncharted territory.
The Washington Post hails Burke as one of the most intriguing minds in the Western world. The New York Times raves he careens from one great moment in history to another.
Where do we want to go from here?
Experience all new connections.
So what's the next connection?
With monthly, annual, and bundled plans, find the one that works for you at curiositystream.com.
This is SpaceTime, Series 23, Episode 63, for broadcast on the 24th of June, 2020. Coming up on SpaceTime, serious questions continue to be raised over science's understanding of cosmic history. A meteor lights up the early morning outback skies of the Pilbara. And SpaceX keeping a busy launch schedule in 2020. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
It's becoming increasingly clear that scientists will need to rethink their understanding of the fundamental history of the universe. A new set of precision distance measurements reported in the Astrophysical Journal has reinforced discrepancies in two competing values for the Hubble constant, which describes the expansion rate of the universe. The value of the Hubble constant is important for testing the theoretical model which describes the composition and evolution of the cosmos. And these new observations were meant to try and reconcile differences between previous measurements for the value of the Hubble constant and the value predicted by the model when applied to measurements of the cosmic microwave background made by the European Space Agency's Planck satellite. One of the study's authors, James Bratz from the National Radio Astronomy Observatory, says galaxies are nearer than predicted by the standard model of cosmology, corroborating a problem already identified by other types of distance measurements. Now, so far the debate's been over whether this problem lies in the model itself or in the measurements that are being used to test it. So to try and resolve the issue, Bratz and colleagues employed a new, entirely different distance measurement technique, one completely independent of all the others. And according to Bratz, it suggests that the basic cosmological model involved in the predictions is the problem. Bratz leads the Mega Maser Cosmology Project, an international effort to measure the Hubble constant by finding galaxies with specific properties that lend themselves to yielding precise geometric distances. Edwin Hubble, the dude they named the telescope after, was the first to calculate the expansion rate of the universe, now known as the Hubble constant, back in 1929 by measuring the distances to galaxies and their recession speeds. See, Hubble discovered that no matter which direction in the sky one looked, the more distant a galaxy was, the greater its rate of recession is. Today, this Hubble constant remains a fundamental property of observational cosmology and a focus of many modern studies. Measuring recession speeds for galaxies is relatively straightforward. Determining cosmic distances, however, has been a difficult task for astronomers. Now, of course, we've covered this before on other editions of SpaceTime, but basically it comes down to this. For objects in our own Milky Way galaxy, astronomers get distances by measuring the apparent shift in an object's position compared to background stars when viewed from opposite sides of Earth's orbit around the Sun. It's an effect called parallax. If you hold your thumb out at arm's length and close an eye, and look at the thumb, open that eye and close the other eye, the thumb will appear to have moved in comparison to the background objects. That's parallax. And you can use that to triangulate the distance to the object. The first such measurement of a star's parallax distance came way back in 1838. But beyond our own galaxy, parallaxes are too small to measure. So astronomers have to rely on objects known as standard candles, so named because their intrinsic brightness is presumed to be known. The distance to an object of known brightness can be calculated based on how dim that object appears from Earth. It's like looking down the road at a bunch of streetlights. You know they're all the same brightness, but the further away the streetlight is, the dimmer it will appear. And by using the inverse square law, you can calculate how far away that streetlight is. These standard candles can include a class of stars called Cepheid variables, as well as specific types of stellar explosions known as Type 1a supernovae. That's because Cepheid variables pulsate, and that rate of pulsation is linked to their intrinsic brightness. And the same goes for Type 1a supernovae. They're all thought to explode with roughly the same mass, and consequently with the same amount of luminosity. And so you can use that brightness to once again determine how far away they are. But another way of estimating the expansion rate of the universe involves observing distant quasars, whose light is bent by the gravitational lensing effect of a foreground galaxy into multiple images. When the quasar's light varies in brightness, that change appears in different images at different times. And measuring this time difference, along with calculations of the geometry of the light bending, yields an estimate for the expansion rate. Based on standard candles and gravitationally lensed quasars, scientists have determined the Hubble constant to be somewhere between 73 and 74 kilometers per second per megaparsec. However, predictions of the Hubble constant based on the standard cosmological model, when applied to measurements of the cosmic microwave background radiation, the leftover energy from the Big Bang, produces a value of only 67.4 kilometers per second per megaparsec, and that's a significant and troubling difference. The difference, which astronomers say is beyond the experimental errors in the observations, has serious implications for the standard model. The model, known as the lambda cold dark matter or lambda CDM, where lambda refers to Einstein's cosmological constant, is a representation of dark energy. The model divides the composition of the universe mainly between ordinary matter, and dark energy, and describes how the universe has evolved since the Big Bang. The Megamaser Cosmology project focuses on galaxies with disks of water-bearing molecular gas orbiting supermassive black holes at the centers of distant galaxies. Now, if the orbiting disk is seen edge-on from Earth, bright spots of radio emission, called masars, sort of radio analogues of visible light lasers, can be used to determine both the physical size of the disk and its angular extent, and therefore through geometry, its distance. The authors use the National Science Foundation's Very Long Baseline Array, the Carl G. Jansky Very Large Array in New Mexico, the Robert C. Byrd Greenbank Radio Telescope, together with the Eifelsberg Telescope in Germany, to make the precision measurements required for this technique. In their latest work, the team refined their distance measurements to 4 galaxies at distances ranging from 168 million to 431 million light-years. Combined with previous distance measurements from 2 other galaxies, their calculations have now produced a value for the Hubble constant of 73.9 kilometers per second per megaparsec. This discrepancy between the predicted and measured values for the Hubble constant points to one of the most fundamental problems in all of physics. Because this method was geometric and completely independent of the others, it reinforces the discrepancy and therefore strengthens the case for a key problem in observational cosmology. All indications now are that the standard model really does need revision. This is SpaceTime. Still to come, a Pilbara meteor lights up the early morning outback skies, and SpaceX keeping up a blistering launch schedule. All that and more still to come on SpaceTime. Okay, let's take a break from our show for a word from our sponsor, ExpressVPN, rated #1 by TechRadar. You may be wondering why you need a virtual private network. Well, it's in the name. It's all about privacy. Do you really want big brother tech companies, hackers, governments, and who knows who else snooping in on your online activities? Now, you might not have anything to hide, but it's still really creepy, and it could be dangerous for you and those you care about. Also, how often do you run across a website and you want to get information from it, but you find out that they're geo-blocked? It's all very frustrating, and it's becoming an increasing problem. And that's where ExpressVPN can help you. ExpressVPN's a simple and efficient way to protect your online privacy. It's internet without borders from the world's leading VPN provider. So, protect your online privacy today. And find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more. And of course, you'll find the link details in the show notes and on our website. That's tryexpressvpn.com/space. And now, it's back to our show.
You're listening to SpaceTime with Stuart Gary.
Well, despite what you may have heard elsewhere, the bright green fireball which streaked across the remote Pilbara skies the other weekend was not space junk, nor the giant asteroid 2002 NN4. It was just a regular small meteor. And it didn't fall to Earth, but rather simply grazed the upper atmosphere before continuing on its journey through interplanetary space. Adrien de Villepoix from Curtin University's Desert Fireball Network says the meteor seen in the Pilbara skies wasn't picked up by its network of 50 cameras, but people from as far afield as Cape Lambert and Hope Downs in the far north of Western Australia, right through to the Northern Territory and South Australia, reported seeing the spectacular celestial light show as it streaked silently across the velvet black early morning sky. Earth's atmosphere is pummeled by around 100 tons of meteors and space dust every day, with that number peaking during meteor showers, such as the current torrids, which, by the way, are made up of larger, more massive meteor material. Think of pebbles instead of dust grains. Usually, blue-green meteors suggest nickel-iron fragments, possibly the cause of once larger differentiated asteroids that have been shattered. But this one was so high up, de Villepoix believes it was more likely to have been electrons from molecules being excited in the rarefied atmosphere. He says the fact that no one reported a sonic boom suggests that it sped through at very high altitude.
People seen across the internet those videos of a giant, bright, green object streaking across the sky. So that's basically all the data that we have that we got to work on and try to figure out what it was. So usually very long fireballs, 30 seconds or so, people and we associate that with space debris. The space debris orbits the Earth and essentially comes back entering into the atmosphere just by skimming off. So a very kind of low, long trajectory across our atmosphere. So this one, me and my colleagues are pretty convinced that it wouldn't be actual space debris. So it wouldn't have been orbiting the Earth before that. It would have been more of a space rock. So a rock that was orbiting the sun and just happened to come on a very shallow trajectory. And we've seen those before as part of the Desert Fireball Network. So the Desert Fireball Network is an Australian project that I'm part of, and what we want to do is put cameras all around Australia to actually record those types of bolides, because they're pretty interesting. Some of these bolides actually drop meteorites, and we got an app where people can report what they see, and in some cases it helps us understand what those rocks are.
So we think this was a space rock that dipped into Earth's atmosphere and then continued on its way through interplanetary space. Is that sort of the idea?
Yeah. So those rocks, if they're basically big enough and strong enough, they can, sometimes, and they come in really shallow trajectory, sometimes they can come back out of the atmosphere, which happens quite rarely, but we've seen one of those on the Desert Fireball Network, and one of my colleague actually published a paper earlier this year about one of them. So it's not unheard of, but basically you need an object that's big enough to be able to kind of pack that punch to actually make it out of the atmosphere. The atmosphere is really good at stopping things. Our atmosphere around the Earth actually stops a lot of rocks from hitting us directly. It's protecting us in a way from those space rocks.
And did anyone hear anything? So it didn't hit the ground, but was there any sort of sonic boom as it flew through some of the thicker layers of the atmosphere, or was it so rarefied up there the speed of sound would have been not an issue?
So from what I've seen, the records, nobody reporting any sonic boom. So that's actually a very interesting point, because that tells us that the rock probably didn't get to the lower layer of the atmosphere. The lower layers of the atmosphere is usually when the rocks come at hypersonics, several kilometers per second speed in there. They create this shock wave, and that's what usually what people hear as a sonic boom. Is that shock wave propagates all the way up to the ground, and sometimes a couple of minutes later, people will hear thunder-like rumbling noises that came from the shockwave. In this case, nobody reported that. That doesn't mean it didn't happen, but that would be an indication that this rock didn't get very far down in the atmosphere. So
there are no infrasound readings either, I take it, from any of the listening posts?
Haven't actually checked the infrasound.
Do we know what direction it was moving in?
It looks like it was moving from a southwest to northeast direction, but it's really hard to tell from just looking at the lights. You basically need kind of reference points in the sky, whether they're stars or buildings, to actually work out precisely which direction this was going.
So we couldn't tell, I take it, whether or not this was part of the torrid stream.
So the torrid stream is actually quite an interesting one. So the torrids are usually a pretty big fireball shower that people can see, usually around October, November time. It's a very, very broad stream. So that happens when a stream of material left over by Comet Anchor encounters the Earth, but it's usually on its inwards direction is when the stream comes from outer space towards the center of the solar system. So it crosses the Earth's orbit and that gets a little bit closer to the sun. But people have also seen some toroids happen in June as well, because obviously the stream, as it comes close to the sun, is going to go back out on its elliptical orbit, and it crosses the Earth's orbit around June time. So it's possible to see toroids, but those would usually happen in daytime. So I wouldn't think this particular fireball could be a toroid. So like June toroids, you'd usually see them during the day or like close to dawn, but not at nighttime.
There's a lot of speculation that the Tunguska meteor event may have been a Taurids stream meteor.
Yeah, there's lots of speculations about rocks, about like all the kind of very kind of famous fireball cases about what stream, or were they even part of the stream, or even what types of rocks they're part of. And that's basically what we're trying to tackle with the Desert Fireball Network, is because there's so much speculation, because nobody actually precisely recorded those fireballs, we basically don't know. And that's what we're trying to do with the Desert Fireball Network, is actually precisely observe the trajectory so we can backtrack what orbits they came from, and maybe associated with a stream or toroid stream or a particular asteroid, and do that sort of stuff. So you kind of need the precise records to do those matches with any sort of like certainty.
One of the things most witnesses have been commenting on is the fact that it was so green in colour. It was quite noticeable.
The colour is actually basically a mix of different things. So interesting thing that people often get wrong is that color is directly linked with the composition of the object, but that's not entirely true, because most of the stuff that you see burning is not actually the rock itself, it's the atmosphere around it. So the color is actually usually telling you more about the atmosphere than about the rock itself. But it's true that in some cases, like iron-rich meteorites might be slightly redder. In terms of that particular green one, most of the fireballs that we see on the Desert Fireball Network appear green, but to be honest, not something that's been studied very much, like the color, the spectrum in general of fireballs. I mean, sometimes we see fireballs like that change colors several times during the flight. So like start green and then go orange and to blue, back to green and orange again. And sometimes it's a little bit difficult to explain, but I'd say it's pretty typical for small space rock to be green.
Sounds almost like the excitation you get in electrons in the atoms of molecules in the upper atmosphere through things like auroral events.
Yes, exactly. That would be representing what the atmosphere is made up there, and not only the rock itself. Exactly.
How does the Desert Fireball Network allow you to study these things as they're streaking across the sky?
So the Desert Fireball Network is essentially a network of cameras spaced about every 100 kilometers or so. So when a fireball comes into the atmosphere, we're able to observe it from different locations, and that lets us triangulate it. So triangulation is a very powerful thing because it lets you pinpoint exactly where the object was, as opposed to roughly know what direction it was. As long as we've got two cameras observing it, we can basically triangulate this thing. So think about triangulation as intersecting planes. Like two planes in most cases will intersect into one line, and that one line is the trajectory in our case. So that's how we track these things. And we can also get speed for those fireballs, and the speed plus the trajectory basically lets us backtrack its orbit. So that's one part of what we do. The other part is we're able to predict where potential meteorites might have fallen. So at the other end of the trajectory, so the meteoroid will slow down to a point where we can't see anymore. It stops ablating. It will go down to just a normal ballistic falling object. At this point here, we can kind of try to predict where it falls on the ground and where we drop a meteorite, and that's when we actually go look for those meteorites. And once we've got that orbit and that rock, we'll be able to study the rock in great detail in the lab. Most of the asteroids that we see in the skies, we've never actually got a chunk of. We can't put them on the microscope. We can't do any sort of advanced analysis on them. That's what the Desert Fireball Network lets us do, is actually associate the rock's orbit, so where it came from in the solar system, with its composition. So that basically gives us a little chunk of an asteroid. Like if it's an iron meteorite, if we ever recover an iron meteorite and know its orbit, we know where the iron asteroids might live.
How long does it take you to get that information uploaded from the cameras to your equipment so you can actually start to track the meteor's path?
So the whole process is actually quite interesting, because it's not really straightforward. There's a lot of things you got to take care of. You've got to calibrate the observations. We first got to detect the meteors. There's a bit of image processing to do. And then got to calibrate the observations with respect to the stars. So that's another step. And then we got to model the trajectory. So basically basically know exactly where it was, how fast it was going, maybe what mass it was. And then we do a whole bunch of weather modeling as well, because in the lower level of the atmosphere, once the rock is slowed down, it will be affected mostly by wind. So we've got to take that into account where that falls. So a couple of years back when we found the first rock, really, it took us probably a couple of days to actually put all of this together because we're fairly new at doing this thing. But nowadays, we can get basically a full position within a matter of hours after it fell, which is great.
And what have you got on this one?
So on this one, our cameras are not located in Pilbara. So we've got some in Wheat Belt in WA. We've got most of South Australia covered, and we've got colleagues at ANU who are developing their own network with the same cameras around Canberra and Sydney. But we're not observing the Pilbara, so we don't have any big data of our own for this one.
Oh no, we've missed it.
Just going to put more cameras out.
How does that make you feel when something that spectacular flies by and you haven't got the equipment to record it? That must be very frustrating.
It is very frustrating. You really feel like those things only happen where you're not looking, and it is very frustrating.
Spare a thought for the Australian astronomer who was at the Anglo-Australian Observatory on a very specific night in 1987, and he was imaging the sky at the time too, and he was pointing towards the Large Magellanic Cloud at that time, just as a supernova occurred. Unfortunately, other things were happening, and he didn't process the data that night, not until the next night, and by the time he had processed his data, supernova 1987 had indeed been discovered by some of his compatriots in other parts of the world.
Yeah, that's the way it happens, and that's what we got to basically, from a hardware point of view, and with all those telescopes, basically push automation for all those systems to actually learn about the cool, exciting stuff really early on. I mean, that's also what gets me going in this project with Desert Fireball Network. Is when I come into the office every morning, I look at the detections from the previous night, and you never know what you're going to find. That's a really cool thing. What type of fireball did you get? And sometimes we go through all that whole reduction process, and we think, it's going to be a 1 kilo meteorite and stuff, just to find out they fell in the ocean, and that's disappointment again. But for the times we actually get it and we actually recover the rocks, is just an amazing feeling of closing the loop and actually make this thing work.
That's Hadrien de Villepoix from the Curtin University's Desert Fireball Network. And this is SpaceTime. I'm Stuart Gary. Now, this Pilbara meteor was just one of 1,220 near-Earth objects, or NEOs, discovered since the start of this year. In fact, 232 have been discovered just in the past month. The European Space Agency's NEO Coordination Centre says that brings the total number of known near-Earth objects, whose trajectories take them close to Earth's orbit around the Sun, to some 22,894 asteroids and 110 comets. And if you want something to keep you awake and worrying at night, be aware that the Pilbara meteor was by no means unique in its closeness. Back on May the 4th, an asteroid now catalogued as 2020 JJ flew just 7,029 kilometres above the Earth's surface. That's far closer than many satellites. The problem is such close encounters are difficult to spot in advance, because the objects that make them are usually really small, often less than 10 metres across. Now that's a good thing, but they're also travelling very, very fast. Now, luckily, they're also rare. In fact, just 16 have been reported coming closer than 3 Earth radii. But 10 of those were in the past 5 years alone. And of those 16, 4 were on a collision course, meaning they entered the Earth's atmosphere and either burnt up in it or went through to hit the surface. Again, luckily, they've all been small. Now, other than 2020 JJ and the Pilbara meteor, 5 other asteroids have come closer to Earth than the Moon over the past month. Another 2020 KB3 came within 3 times the Earth-Moon distance, while 2 others, 2008 TZ3 and 2009 XO, each around 300 metres wide, flew within 8 lunar distances. As for that 400-metre-wide asteroid 2002 NN4, well, just as predicted, it passed the Earth safely on June the 6th at a distance of approximately 5.1 million kilometres. That's some 13 times further away from the Earth and the Moon. This is SpaceTime. Still to come, SpaceX keeping up a blistering launch schedule. And later in the science report, a new study confirms the use of face masks has been effective in reducing the transmission of COVID-19. All that and more still to come on SpaceTime. SpaceX has been maintaining a busy launch schedule, with another Falcon 9 rocket successfully lifting off, carrying 58 more Starlink internet communication satellites, as well as 3 new SkySat Earth observation spacecraft. The Starlink 8 mission flew from Space Launch Complex 40 at the Cape Canaveral Air Force Station in Florida. The flight came just days after the Starlink 7 mission blasted off from the same launch pad, and just weeks following the Demo 2 mission, which carried SpaceX's first crew to the International Space Station from the nearby Space Launch Complex 39A at the Kennedy Space Center. Following the launch, the boosters successfully landed on the drone ship Of Course I Still Love You, which had been pre-positioned downrange in the North Atlantic Ocean.
LD is go for launch.
And there's that call out for go for launch.
Falcon 9 is configured for flight.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Liftoff of Falcon 9 and Starlink 8.
And Falcon 9 has just had a successful liftoff.
Telemetry are nominal.
A successful liftoff from Pad 40 for its first Starlink rideshare, carrying 3 Planet SkySats and our SpaceX Starlink satellites. Next coming up will be Max Q.
Mach 1.
And that is the maximum aerodynamic pressure that the vehicle sees, the largest structural load that the vehicle sees throughout ascent.
Max Q.
And there's that call out that we just passed through Max Q. Next up will be 3 events happening back to back, and that will be MECO, or main engine cutoff, stage separation, as well as second engine start, or SES-1. Main engine cutoff, or MECO, is when all 9 of the M1D engines shut off and slow the vehicle down in preparation for the next event, which is stage separation. And stage separation is where the first stage separates from the second stage, with first stage making its way back to Earth and second stage taking our satellites to their targeted orbit. And then finally will be SES-1, which is second engine start, with that MVAC engine lighting up and taking those...
Vehicle is following a nominal trajectory.
And taking those satellites to orbit.
MECO. Stage separation confirmed.
MECO, main engine cutoff, and stage separation. Second stage with that MVAC engine glowing bright red there. Those grid fins deploying on the first stage. Those grid fins help.
Fairing separation confirmed.
And we just had fairing separation. We had a successful deployment of those fairing halves. Let's see if Miss Tree and Miss Chief can make a catch attempt today.
Vehicle continues to follow a nominal trajectory.
And as I was mentioning, the grid fins have deployed. That helps guide that first stage back to its landing zone.
Acquisition of signal Bermuda.
Stage 2 is still looking good. And coming up next for first stage, as it makes its way back to Earth, it will perform a couple of burns, the first of which will be the entry burn. And that entry burn is where 3 of the 9 Merlin 1D engines light up and slow the stage down as it re-enters back into the upper part of the Earth's atmosphere. The second burn is called the landing burn, and this is when the single engine on the vehicle, the E9 engine, ignites and brings the vehicle speed down rapidly in order to land on the drone ship. And again, we are attempting to land on our drone ship, Of Course I Still Love You, today. Second stage is still looking good.
Vehicle continues to follow a nominal trajectory.
And again, that first stage is making its way back to our drone ship, Of Course I Still Love You, to its landing zone.
Stage 1 FTS is saved.
Stage 1 entry burn has started.
The entry burn will last about 20 seconds long. Stage 2 is still looking good. We're just about a minute away from that landing burn.
Signal first stage from the Cape expected.
And we did hear that call out that we did lose that live signal of the first stage as expected. Coming up here in at about T plus 8 minutes and 21 seconds will be the beginning of the landing burn. Landing burn will last about 20 seconds long. And then hopefully first stage touchdown on our drone ship, Of Course I Still Love You.
Stage 1 is transonic.
About 10 seconds after landing of the first stage will be SECO 1 on second stage. So we will have a couple events happening very close to each other. So we'll listen in and wait for those call outs.
Stage 2 has entered terminal guidance.
Stage 1 landing burn has started.
And that landing burn has begun on the first stage. Again, this will last about 20 seconds long. Let's booster
Stage
for
2
a third
FTS
time.
is saved.
Stage 1 landing legs have deployed. Stage 1 is landed. Landing operators proceed to 11.100 on recovery 1 and ETF 9.
Stage 1 has landed on Of Course I Still Love You. We are waiting for stage 2 for SECO 1, which is second engine cutoff.
Nominal orbital insertion.
All right, starting TX Prime RF1A on.
We did confirm SECO and confirmed good orbit. So now that second stage is going to coast in this orbit for a few minutes.
The flight was the third launch for the same Falcon 9 booster, which had previously flown on the CRS-19 Dragon resupply mission to the International Space Station, that was in December 2019, and the CRS-20 Dragon cargo mission to the orbiting outpost in March this year. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. A new study has confirmed the use of face masks has been effective in reducing the transmission of the COVID-19 coronavirus. The findings, reported in the Proceedings of the National Academy of Sciences, shows how airborne transmission plays a major role in the spread of the deadly virus, which has now infected more than 8 million people worldwide and caused more than 500,000 deaths since spreading globally from its Wuhan epicenter in China. Comparisons of COVID-19 infections in both Italy and New York City before and after the implementation of mandatory face mask use suggested the measure prevented more than 78,000 infections in Italy between April the 6th and May the 9th, and more than 66,000 infections in New York City between April 17th and May 9th. Meanwhile, a second study, this one reported in the Journal of the Proceedings of the Royal Society, has found the widespread use of face masks, together with the implementation of lockdowns, is causing vastly less disease spread and a flatter second or third wave of COVID-19 infections. A new study conducted over 32 years in the United States suggests that it's not necessary to conform to a single diet in order to achieve healthy eating, and that following a range of healthy eating patterns may lower your risk of heart disease. The findings, reported in the Journal of the American Medical Association, looked at the diets of around 200,000 people and then scored them based on how they complied with 4 different types of healthy diet, from more Mediterranean diets to more plant-based ones. Researchers found that those who scored higher on all 4 dietary scales had lower cardiovascular risk. Healthy diets all share several common components, including a higher intake of whole grains, vegetables, fruits, legumes, and nuts. A mysterious cloud containing radioactive ruthenium-106, which moved across Europe in 2017, most likely originated from a Russian-designed civilian nuclear plant. European radiation protection authorities found concentrations of the radioactive substance reached 100 times higher than the levels detected over Europe following Japan's Fukushima nuclear reactor meltdown. However, no government's taken responsibility for the radiation release, and it's been assumed that it may well have been from the production of military weapons-grade plutonium. But a new report in the journal Nature Communications has now ruled out military sources, instead finding that the radioactive cloud was released from a plant reprocessing nuclear fuels. The authors used high-precision mass spectrometry measurements from the clean chemical separation of ruthenium fractions from air filters to find the airborne radioactive ruthenium had been diluted with natural stable ruthenium. They determined that the ratios of the ruthenium isotopes were consistent with spent nuclear fuel from a nuclear power plant. And they were able to narrow it down better than that. The isotope signatures showed that they didn't originate from nuclear fuels used with Western pressurized or boiling water reactors, but were instead consistent with the isotope signatures of a Soviet Union or Russian VVER series pressurized water reactor, approximately 20 of which are still in operation. In fact, we can even tell you where they are. VVER nuclear power stations have been built across Russia and the former Soviet Union, as well as in China, Finland, Germany, Hungary, Slovakia, Bulgaria, India, and Iran. Now all they've got to do is correlate concentrations with wind patterns at the time, and we'll have our culprit. A new study has confirmed something most pet owners already know. Dogs are aware when they're being treated unfairly by their humans. And while all dog breeds are aware of it, it seems different breeds do react differently. A report in the journal PLOS ONE looked at 24 poor little puppies who were teased with unfair treatment and then had their responses monitored. Dogs, cats, and many other animals are known to display negative responses to unfair outcomes. For this study, researchers looked at 12 dogs from cooperative working breeds, such as Aussie Shepherds, Border Collies, and Labrador Retrievers, and 12 from independent worker breeds, such as Siberian Huskies, and then examined their responses when 2 dogs were asked to give their paw, but only 1 dog was rewarded afterwards. None of the participants were happy with the, dare I say, rough treatment. But the cooperative breeds seemed to be working longer under these unfair conditions. But the independent breeds gave their paw far less, especially when delicious treats weren't involved. And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from SpaceTimeWithStuartGary.com, or from your favorite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through SpaceTimeWithStuartGary.com for all the details. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.